Before we get into our note on critical points, I thought that I'd give you a quick little warm-up and get you thinking about some of these functions. So we're going to consider the graph of the function f of x is equal to x minus 2 times x plus 4. Right away, I hope you all recognize that that is a quadratic. And since it's in factored form, we are able to just quickly sketch this out. So we know that we have a root at positive 2. And we know that we have one at negative 4. Now, since I have a root at positive 2 and negative 4, I know that my vertex is going to be halfway between there at negative 1. And if I plug negative 1 into the equation, I can find my vertex, and it's going to be down here at negative 9. If I use my step pattern, I could go ahead. I don't even really need to do that. I have 3 points, so I could connect those to get my graph. I could also figure out my y-intercept by plugging in x's of 0, and that would be at negative 8. So that would be another point that I could add on to there. So the next thing that I want you to do is think about where on this function is it increasing. So maybe you need to pause the video, maybe you can think about it right now. But where on this graph, as you read from left to right, are these y values increasing or getting bigger? After you're done thinking about when it's increasing, I want you to also think about when is it decreasing. So again, reading from left to right, what interval is this function, does this function have y values that are going down? So take a second, pause the video, and then when you're ready, hit play again. So when I look at this graph, I notice that to the right of my axis of symmetry, all of these y values are increasing. You're going to see me draw some dashed lines here. Picture a pencil moving up along this function, and you would see it always has a positive slope, and it's always an increasing y value. So I can write this as x is greater than negative 1. Anything past an x value of negative 1, this function is increasing. The exact same thing would go for decreasing. So if I look to the left of that negative 1, everything along here, the y value is getting smaller. So for the increase or decreasing, it would be x is less than negative 1. The next thing that I want you to take a look at is how could you use the derivative of this function to examine these intervals? Typically, you won't have a graph before you have to answer these questions, and so we need to think about how could we use the derivative to answer these questions, and then we'll use that information to help us draw a sketch of something. We know that if we take the derivative and set it equal to 0, that's going to give us our maximums and the minimums. And then we could use that information to create a table and see if to the left and right of these maximum and minimums, if our function is increasing or if it's decreasing. Keep in mind this is a very basic example, and so it was easy for us to take a look at this equation in factored form, plot those roots, see where the middle of that would be, and we were able to easily calculate our vertex from that. But if it wasn't so easy, or if you didn't want to do it like that, we could expand this out, so x squared plus 2x minus 8, and like I was saying earlier, if we take that derivative, so 2x plus 2, and we set it equal to 0, we are able to, negative 2x equals 2, we are able to get that x value of negative 1 this way, which we know is that critical point, either a maximum or a minimum. And then if we were to do f of negative 1, we would get the negative 9 that we previously got for the vertex. Just one quick thing I wanted to note, that you do know how to take the derivative of this function. It is probably just easier to do the derivative from the standard form versus the factored form, but if you don't want to do that and you want to use the factored form, that is okay as well. Now that we've determined this point, we're going to call this a critical point. We are able to start this chart. This is part of our analysis, and this is what you're going to do for all of the questions from this point forward. So we're going to create this chart with our derivative f prime of x and our original function f of x. We're going to plug in our critical points. In this case, we only have the 1. And then we're going to take a look at what's happening to the left of that critical point and to the right of that critical point. Now we know that at that critical point, the derivative was equal to 0. If we think about what's happening in our original function, we know that the slope of the tangent at that point is going to be horizontal or 0 as well. The next thing that I'm going to do is choose a test value, one from the left and one from the right, and we're going to see what's happening. I'm not expecting you to write your test value down, but it is a good idea just at the beginning. So I'm going to choose some value less than -1. So I'm just going to choose -2. If I plug that into my derivative, so into this function right here, I'm going to get 2 times -2 plus 2. That's going to give me a negative value. I don't care what the value is, I just care whether it's positive or negative. So what this means is that this function is going to be decreasing or have a negative slope. I'm going to do the exact same thing over here. I'm going to choose a test value that is bigger than -1. In this case, I'm going to choose 0. Whenever possible, choose 0. Plug that in, and I'm going to get 2 times 0 plus 2. So this is going to give me a positive result, which is going to give me an increasing value or a positive slope. All right, so in this first example, we are going to be determining the intervals of increase and decrease for the following function. F of x equals 2x cubed plus 3x squared minus 36x plus 5. So the first thing that we're going to be doing is finding the derivative of this function. So 6x squared plus 6x minus 36. I'm going to set that equal to 0. And then we're going to factor. I can take a 6 out right away. So x squared plus x minus 6. And then something that multiplies to -6 and adds to 1. X plus 3 and x minus 2. So I know right away that I have a critical point at x equals -3 and another at +2. So now that we have these critical points, we're going to start doing an interval chart. So as you can see here, I have included the critical points. So I've included this -3 and I've included this 2. And then some students find this easier to think about a number line, but basically I need to include any interval besides those. So I have the interval less than -3. I have the interval between -3 and 2, and then I have the interval greater than 2. Now for the rest of the chart, you can see that I have something called test value. This won't be necessary later on, but since we're just starting, it's a nice addition to the chart just so that you remember what value you're plugging in. And then we are going to plug this into the derivative, so f prime of x, and then again our f of x, our original function. So obviously this test value is just -3 and this is just 2. It's important to know and see what's happening at these critical points. And then we want to choose a test value that is less than -3. I always just go one less, so -4. Here we want to choose a test value that's between -3 and 2. If possible, you always want to choose 0. You might as well get some more information about some y-intercepts while we're at it. And then we want to choose a test value that is greater than 2. So again, I'll just go one above and we'll do 3. So now that we have these intervals and these test values, what we need to do is we need to start plugging them in. So in the next row, we need to plug these test values into our derivative, into our f prime of x. So if I do f prime of -4, I'm going to get 36. Now, normally I don't show this line, but again, it's a note, so I wanted to show you exactly what I was doing, and maybe for the first little bit, you'll show it too, just so that you can look back and remember. All I really care about here is that I got a positive number. So in the chart, eventually, all you'll need to show is this sign or this positive. If I do f of negative 3, sorry, again, f prime of negative 3, I'm going to get 0. I know that. It was a critical point, so that's a big 0. The exact same thing will happen here for an x of 2. Now, if I do f prime of 0, which 0 was my test value, I'm going to get negative 36. Again, I don't care about the number. All I care about is the sign. And then f prime of 3, I get 36. And again, I just care about this sign. So now that we have this information, we can talk about what it means for our original function. If our derivative is positive, that means that my original function is increasing. If the derivative is 0, that means that my original function is horizontal. I'll just draw this horizontal line here. When it's negative, it's decreasing. So again, I've got a 0, so a horizontal line, and then a positive, so an increasing line. So the last thing that I'm going to do on this slide is just kind of write a little summary of what's going on. I know that f of x is increasing on 2 intervals, so it's increasing here, so x is less than negative 3, and it's increasing here, x is greater than 2. I know that the function is decreasing on this interval right here, so negative 3 less than x less than 2. At this time, we can start doing a quick sketch, which I will start on the next page. So what I've done here is I've just rewritten these intervals of increasing and decreasing for you, and I rewrote our original function. This is not a nice function in terms of zeros, and if I was asking you to do a sketch for me without technology, I would make sure that it was factorable and that it was nice. If I gave you something like this and I expected a sketch, I would absolutely say use technology. So I will always tell you if that's the case. So when I look at this function, I do know that I have a couple of important points. I can find my y-intercept, so plugging a 0 in for all of these x's, I could see that I have a y-intercept at 5. I know that I have some critical points. I know that I have one at negative 3 and 2. I don't know why I wrote a negative there. Negative 3 and positive 2. If I plug those into my original function, you can go ahead and use a calculator. For negative 3, I will get 86, and for 2, I will get negative 39. And then again, because this is not factorable, it's not nice, I'm going to say feel free to use some technology, and you'll see that your roots are at negative 5.1, 0.14, and 3.5. So with all of this information, I am able to draw a quick sketch of what's happening here. So I'm not going to include a lot of detail. This is just a very quick sketch. I know that that y-intercept is at 5. I know that I have this one root at 0.14. I know that I have another one at 3.5 and another at negative 5.1. So what is happening here? I guess I should include this other point. Negative 3 and 86, so way up here, and then a 2, negative 39, so down here. All right, this is kind of like a connect the dots. So we know that before negative 3, so up until negative 3, our function is increasing. So it's going to start way down here. We know it has to go through this root, and it's going to be increasing up until we reach this maximum at negative 3. We know that between negative 3 and positive 2, this function is decreasing. So it's going to be going back down. It has to go through that y-intercept. It's going to go through that root at 0.14, and it's going to hit this minimum at positive 2. And then we know that after 2, our function is increasing again, so it's going to go back up again through this root, and this is a quick sketch of our graph. In the next video, because I'm cut off at 15 minutes, I am going to go over some more information about critical points.